In this video, I will show you how to evaluate a limit indirectly using the traditional and alternate definitions of a derivative. The traditional definition of derivative looks like this. F prime at c is going to equal the limit as h approaches 0 of f at c plus h minus f at c all over h. The alternate definition of derivative looks like this. F prime at c is equal to the limit as x approaches c of f of x minus f at c over x minus c. So you'll notice that the alternate definition of a derivative really looks like an old school slope where you have y minus y over x minus x. Just as you're memorizing these, notice that both versions have f at c in the upper right hand position. So if they give me a limit that fits one of these two patterns, instead of trying to directly evaluate it as a limit, I'm going to rewrite it as a derivative and then use my derivative rules. So in this case, does this problem remind you of the traditional definition or the alternate definition? So in the denominator, I see this x minus pi, which looks like x minus c. So I'm going to compare to the alternate definition of derivative. For the alternate definition, as I mentioned, in the denominator, this would be x minus c. So if this turns out to work, then that means that the c value must be pi. For the alternate definition, in the numerator, you have f of x minus f at c. So next, look where the f of x goes, and you see this cosine of x. So if this is going to work out, that means that f of x must be cosine x. So you have to check one more thing to be sure that you're really looking at a derivative. And that is, you need to check f at c and see if you really get the value that's sitting right here. So we know function f, and we know the value of c is pi. So f at c, in this case, will equal f at pi, which will be the cosine of pi. And picturing your unit circle, you know that pi is right here. Cosine is the x value, which is -1. So f at c equals -1. Does that match what we have here? Well, it does, because we have to do f of x minus f at c. So if we do cosine x minus -1, then that makes cosine x plus 1. So everything matches, which tells me that this limit is really a derivative in disguise. This limit is really f prime at c, where function f is cosine and c is pi. So we just need to find f prime at c. So first we need to find the derivative f prime. But the derivative of cosine is negative sine. So that's f prime. F prime at pi is going to be negative sine pi. And sine of pi, sine is the y value, and at pi, the y value is 0. So this is like -0, which is just 0. Which means that the final answer is A. The moral of the story is that for a limit like this, rather than trying to evaluate the limit directly, it's a lot easier to recognize that this is really a derivative in disguise. So we can just use our derivative rules instead. Problem number 2 should be reminding you of the traditional definition of derivative, because you see that h in the denominator. H approaches 0. So for the traditional definition I showed you a minute ago, in the numerator we have f at c plus h. And then in the second position we have minus f at c. If you compare these expressions, you can probably see that the c value must be e. In both of these expressions, you see the e right here, and then you see the c right here. So we can be pretty comfortable that c must equal e. We can also tell what the overall function must be. Right here we have e to the e power. So you can bet that f of x must be e to the x power. And we've just simply plugged in e in for x. Okay, if we plug in e right here, then we have e to the e power. For this first term, if you plug in e plus h, right, because that would be c plus h. If you plug in e plus h right here, then that would give you e to the e plus h power. So either way, we see that f of x must equal e to the x power. That means that this limit is a derivative in disguise. So this is just a fancy way of writing f prime at c, where the function f is e to the x power and c is e. So rather than trying to evaluate this limit directly, let's evaluate this derivative instead. So let me start over though. So starting with f of x. So we have f of x is equal to e to the x power. Now let's find f prime. Well, the derivative of e to the x is just e to the x. It's the simplest derivative rule of all. But now we want to evaluate f prime at c. So in this case, that means we want to evaluate f prime at e. All right, because that's what this limit really means. So we're just going to plug in e. So that would give us e to the e power. And that's it, guys. The answer should be e to the e power. And so that is option C. For number 3, it looks like we are going for the traditional definition of derivative, because that's the one that has h in the denominator. So remember, in the numerator of the traditional definition, we have f at c plus h, and then minus f at c. So somehow I have to get this to match up with this. So obviously we have the tangent sitting here. So my first thought was, okay, what if f of x was simply equal to tangent x? Well, I'm not seeing how I'm going to get a 3 in there unless I put a 3 in here. So let me modify this and call it tangent 3x. All right, so let me come back to this. Now let's talk about the value of c. So if f of x is equal to tangent of 3x, then what about f at c plus h? So f at c plus h would then be the tangent of 3 times c plus h. All right, but notice on the inside here, all we have is 3h. Okay, there's nothing extra being added on. So that suggests to me that maybe c is 0. So imagine that for a second. Let me put this off to the side. What if c is 0? So let's see if this traditional definition of derivative will morph into this if f of x is tangent 3x and c is equal to 0. If f of x is tangent of 3x, so I'm about to do f at c plus h. So that's going to be tangent 3x, all right? I'm putting parentheses instead of x so that I can put c plus h inside. But remember that c is 0, so this is like 0 plus h. And then we're going to do minus f at c. So and function f is tangent 3x. So I'm going to have tangent 3 at 0. But 0 plus h is just h, so I wind up with tangent of 3h, which is what I have here. And then tangent of 3 times 0 is really just tangent of 0. And tangent of 0 is 0. So that's why this term is missing. All right, so that means that this does fit the traditional definition of derivative if f of x is tangent 3x and we are evaluating at c equals 0. So that tells me that instead of evaluating the limit directly, if I wanted to, I could do a derivative. Okay, so we can do this. Like we said a minute ago, f of x is the tangent of 3x. What we have to find is f prime at c, okay, and c is 0. So we can just do f prime at 0, and that will be the value of the limit. Okay, we can do a derivative instead because this is a derivative in disguise. So let's do f prime. We know that the derivative of tangent is secant squared. So this will be secant squared 3x. Of course, we have to do the chain rule because we have this inner function here. So we have to multiply by the derivative of 3x, which is just 3. All right, so this is f prime. So now we're going to do f prime at 0. So that's going to be, I'm going to put the 3 in the front. It just makes me happy. So this will be 3 secant squared. And then we're substituting 0 here. So I have 3 times 0. That will be f prime at 0. So I just need to evaluate this. But 3 times 0 is just 0. So I have 3 secant squared 0. But what is the secant of 0? Well, let me answer your question with a question. What is the cosine of 0? Picturing the unit circle, cosine is right here. That is 1. So the cosine of 0 is 1, which means that the secant of 0 will be the reciprocal of 1, which is 1. Which means that secant squared is also 1. All right, so this is really going to equal 3 times 1, which is 3. So therefore, the answer is B. By the way, if this were actually the AP exam, we probably would have solved this using something called L'Hopital's rule. I did not use that here because we have not learned that yet at this point in the course. All right, but if you already know L'Hopital's rule and you were screaming at the TV, screaming at your phone, whatever you're watching this on, and you're going like, why don't you just use L'Hopital's rule? That's why, because we haven't learned it yet. Problem number 4, if f prime at 8 exists, then it can be found by evaluating which of the following limits. So this is exactly what we've been talking about. So really look through these options, and you're looking for the traditional definition of derivative or the alternate definition of derivative when we're dealing with the function f of x and the value c is a for this problem. So let's see. For the traditional definition, we have f at c plus h. So in this case, it'll be f at a plus h, and then minus f at c. All right, so f at a, all divided by h, and the limit as h approaches 0. So option number 1 is just a straightforward presentation of the traditional definition of derivative. So we could definitely find f prime to evaluate this limit. So which one of these is going to be the alternate definition? So look at option number 2. Option number 2, we are supposed to have the limit as x approaches c. Well, we have this a instead, which is fine. And then we have f of x minus f at c. So we have f of x minus f at a. So that matches. And then the denominator is supposed to be x minus c. So x minus a then. So this is the alternate definition of derivative. Option 3 does not match either of our definitions for derivative. So we are looking for the choice that says option 1 and 2 only. So the answer is C. Let's do one more. Problem number 5, it looks like we are again shooting for the traditional definition of derivative. And I see a natural log of some stuff. So probably f of x is going to equal the natural log of x. Let's start off with that and see how far we get. For the traditional definition, inside we have to have f at c plus h. So that would suggest that c is e. So I'm going to write that down off to the side as well. Okay, c is equal to e. So let's set up the traditional definition and see if it matches what we have. So we would have the limit as x approaches h of, and we need f at c plus h. All right, but in this case, that's going to be the natural log at c plus h. So that would be e plus h. And then we have minus f at c. Okay, so that's going to be minus the natural log at e. And then in the denominator, we just have h. So far, this part matches this part. And we do know that the natural log of e is 1. So it all matches. So that means that instead of evaluating the limit directly, we can just find the derivative and evaluate that at e. So that's what we're going to do. So let's do f prime. The derivative of natural log is 1 over x. All right, that is just something that we have memorized. So then f prime at e will be 1 over e. So that's it. The answer is D. Isn't that easy? By the way, a minute ago when I said that the natural log of e is equal to 1, if anyone did not already have that basically memorized, it's because the natural log is log base e. So natural log of e would be log base e of e. So you're asking yourself the question, e to what power is e? Because that's what logarithms mean. Well, e to the 1 power is e. So that's why the natural log of e is 1.